Hello, today we are going to study the chapter local maxima and local minima for a single variable, right? So let's get the idea first. What is local maxima and local minima? Suppose if I draw a graph like this, this is y-axis and this is x-axis, and I draw any curve on it, any curve this, like this, right? And if I take the region from here to, let's say, here, right? I am taking this region, right? So it is clear from the graph that this one here, this point right here, is a local minima, and this point right here is a local maximum, because in this region we see that there is no other points greater than this, and there is no other points less than this, right? To make it clear, I will do this. I will just see the graph. See, there is no points in this region from here to here. In this region there is no points lesser than this point, and same case here. In this region from here to here, from here to here, there is no points which is greater than this, right? So this, from this area, this whole area, right, it is, we get the, this is the local maxima, and this is local minima. This color is so, anyways, you get the idea, right? What is local maxima, what is local minima? Now let's come to the point how we can solve a function and how we will find the local maxima and minima from a given function, right? So let me write the steps to find the local maxima and minima, minima from a given function. Now again, another point, why it is called local? Why it is called local? Because we don't know that this is a starting point or ending point. It may go up like this and it may go down like this. So this is not the global maxima or global minimum, because the curve can rise after this and the curve can fall before this or rise before this or whatever. So this is not the global maximum minimum, because we are considering a region. In this region, this is a local maxima and this is a local minima. Therefore, we are calling it local, right? It is bound by a region. So now, yeah. So step one to find the local maxima and minima from a given function. To find the local maxima and minima, we need to get the critical points. We come to the concept of critical points later, but first step is actually we need to partially differentiate the function with respect to x. What does it mean? We need to simple partial. It is understandable, quite understandable. Now, what is partially? Partially actually means, what is partially? Partially actually means that we will only differentiate those variables or those constants which are attached or which have a variable x or any other variable which is a part of the objective function. Okay, so yeah, you get the idea. Now, after partially differentiating, we need to put the function equal to 0. So after partially differentiating, we get an equation, and we need to put that equation equals to 0. Okay. So after putting that function equals to 0, we get no. After solving, we get some values of x, which is actually the critical values. Right. This is the step 1. It is pretty easy. First, partially differentiate the function with respect to x or any other variable. After that, partially differentiating. After that, we need to put the equation equals to 0, and after the solving, we get the value of x or any other variable. Right. Sorry. And now step 2. We move towards step 2. In step 2, we need to find the inflection point. Now, what is inflection point? Inflection point is a point where a curve changes its curvature. We will learn more about inflection point in the example I will give later on. Right. So, how to find the inflection point? Then we need to find the second order. In order to find the inflection point, we need to find the second order partial derivatives of the function. We need find the second order partial derivatives of the function. And here I can write that del y by del x equals to 0, right? Yes, you know that del y by del x is the partially differentiating the function with respect to x, or you can say del f. If the function abbreviation is given with f, you can write del f by del x. You know what, I will change this to del f because it's more appropriate. Yes. So del f by del x equals to 0, right? Then when step 2, we come back to step 2. Step 2, we need to find the second order partial derivatives of the function, and del square y, or this is f del x squared equals to 0. After putting that, we need to find some. Then we need to find the values of x, which actually will give us the inflection points. We'll come back to this term of inflection point later on this video. Now just find the second order partial derivative, put it equals to 0, and find the value of x, right? Second step is this. It's also very easy, right? Now comes the third step. So what is the third step? Step 3. Step 3, right? So what is the third step? The third step is that we need to set the second order partial, I'm not doing this right. So we need to set the critical points into the second order partial derivatives to check whether the curve is concave upwards or concave downwards. Now you might see at first the step and tell that it's pretty confusing, but it's also very easy. See, we get the critical points in step 1, right? Here we get the critical points, critical values or critical points, whatever. So here we get the critical points, and we simply put those value of x in the second order partial derivatives. The second order partial derivatives, we put those values in the second order partial derivatives, and we get some values, right? After putting the value of x in, after putting the value of x, that is critical values of the values of x. So after putting those values in the second order partial derivatives, we get some values. After that, we need to check if the values are positive, if the values of, if the critical point values after putting in the second order partial derivatives gives a positive value or a negative value. If the value is positive, it is concave upwards. If the value is negative, it is concave downwards. How will see? See, if after putting the critical values in f double dash x. So yeah, if after putting the critical values in f double prime x, which is the second order partial derivative, this means a second order partial derivative, right? If, sorry, this color is not good at all. If f double dash x greater than 0, it is concave upwards, right? Or the curve is concave upwards. It might seem a little bit confusing, but it's very easy, trust me. After showing you an example, it will be very much clear to you. If f double dash x less than 0, then the curve is concave downwards. We will get to this, right? And we are done. After that, we will simply find out, fx for x greater than 0, x less than 0, and x equals to 0, and plot them on the graph, and we will get the local maxima and the local minima. So let me revise the steps once again. We get the concept. And step 1, first we need to partially differentiate the function with respect to x, that is del, and then we need to put it equals to 0, that is del f by del x equals to 0. We get the critical values. After solving, we get the critical values. Then we need to second order partial derivatives of derivate the function, or find the second order partial derivatives of the function. Del square f by del x square equals to 0. We get some values, and those are the inflection points. And then at the third step, we need to put the values which are obtained here, that the critical values into the function, into the second order partial derivatives, into the functions we obtained from here, like from this part, this area, only this much. We need to put those critical values in this equation, and we will get some constant values. If the values are positive, then the curve is concave upwards. If the value is negative, the curve is concave downwards, right? And after that, we need to plot all the 3 points in the graph, all the 3 coordinates in the graph, and we will get the local maxima and local minimum. How? I am showing an example, and it will be very, very much clear to you. So now let's get to the example. So example, and after solving and after doing this example, all the concepts about local maxima and minima will be just totally clear to you. How? Let's see. Let a function be given, fx equals to xs cube minus 3x. A simple function, and we need to find the local maxima and minima of this function. So what are the steps? Step 1, we need to find the critical points, right? So first we need to find the critical points, right? First we need to find the critical points. So therefore f dash x, by the way, f dash x stands for del y equals to del f by del x. This stands for this, okay, equals to, how can we partially differentiate it? So CF will be here and the power will be 2, right? So 3x square minus 3, because the derivation of x equals to 1, right? So yeah, now we need to set the first order partial derivatives equal to 0, right? So f dash x equals to 0, therefore 3x square minus 3 equals to 0, x square equals to 3, 3x square equals to 3, x square x square equals to 3 by 3 equals to 1, x equals to root over 1 equals to plus minus 1, therefore x equals to 1 or x equals to minus 1, right? We get the critical values. These are actually the critical values. As I said, these are the critical values. Okay, we get the critical values. We need to find next step 2, as we know, to find inflection point, we need to find the second order partial derivatives, right? So we need to find second order partial derivative. Let me write it. We need to find the second order partial derivatives. So f double dash x equals to del square f by del x square, actually this stands for this, okay, equals to so we have got this function and we need to again partially differentiate this. As this is a constant, this is equals to 0 and we have 2 into 3 and x will be x to the power 2 equals x to the power x, right? So right, therefore inflection point right, inflection point, we, how to find the inflection point? If double dash x equals to del del square f by del x square equals to 0, right? We need to put the second order partial derivative equals to 0. So 6x equals to 0, therefore x equals to 0. So the curve changes its curvature, the curve changes its curvature at x equals to 0, right? The curve changes its curvature x equals to 0. How? When we will plot it on the graph, we will see that it changes its curvature x equals to 0. Okay, so next step. Now we need to put the critical points in the second order derivatives to check the slope. We need to put the critical points in the second order partial derivative check the slope, that is whether it is concave upwards, upwards or concave downwards. So what critical points we obtain? We obtain that the critical points are x equals to 1 or x equals to minus 1. And sorry, what is the second order partial derivative? 6x, right? So therefore f double dash 1 equals to 1 means we are putting the values critical value 1, 6 into 1 because it was 6x, 6 into 1 equals to 6, which is greater than 0. Therefore positively sloped, concave, and we can also write this as concave upwards. And f double dash minus 1, when critical value is, we are taking the critical value minus 1, equals to 6 into minus 1 equals to minus 6, less than 0, right? Therefore negatively sloped. Therefore concave downwards. Simple, right? Yeah. After that, we need to put the critical values in the main equation and also the value of the inflection point in the main equation. What is the main equation? Sorry. What is the main equation? The main equation is actually this one. So we need to put the values, critical values, and the value of the inflection point in that equation. So putting the critical values and the values of the inflection point in the objective function. What is the objective function? X cube minus 3x, right? I'm just writing it for reference, x cube minus 3x, right? So if 1 is one of the critical values, so if 1, when x equals to 1 cube minus 3 into 1 equals to minus 2. Putting in this equation, right? Putting 1 in x equals to 1 in this equation. Second, if minus 1, when x equals to minus 1, because we also get a critical value minus 1. So minus 1 cube minus 3 into minus 1 equals to 2, right? We get the value 2. And lastly, when f equals to 0, when x equals to 0, f 0 whole cube minus 3 into 0 equals to 0. Okay, so now we get the maxima, local maxima and minima by plotting the graphs, right? So we will plot the graph simply by, to plot a graph we will also draw negative axis because we get some negative values, right? Like this and this. So x and x dash, sorry, I'm writing it wrong, like y and y dash, x dash x, like this. And we get 0 here, 1 here, 2 here, and 1 here, and let's say little more, sorry, little more, 2 here, and minus 1 here, and minus 2. Just drawing it roughly, minus 1 and minus 2. Now let me draw the graph. Okay, so where is where the function is x equals to 2. So 2 when x equals to -1, right? Y equals to means function equals to 2 when x equals to -1. So we get here that when x equals to -1, y equals to 2. We get a point here. Just like this. Right? After that, we get when x equals to 1, y equals to -2, because the function is equals to -2. Yeah. Y equals to -2. So we get a local maxima here. We get a local minima here. And as we know that the point here, it is what? It is concave upwards or concave downwards. We get here the slope is concave downwards, because at -1 the slope is concave downwards. So it is the local maxima. And as we go down here, passing from the point 0, my drawing is not that good, but you will get the idea. And after point 1, we get local. We get that the slope that the curve is concave upwards, so it will go upwards like this. So it was here the curve is downwards, here the curve is upwards. Let me draw with another color. We'll get better idea. Not this color. Okay, this is upwards. It's going down first, because at -1 the curve is concave downwards. We have seen that by second order partial derivatives, right? And putting in 0, we have seen by putting the critical values that the slope is concave downwards, and here we have seen that the slope is concave upwards like this, right? So here we get local maxima, and here we get local minimum, right? And this, my friend, is the inflection point. Now, as I said, I will explain. Let me now explain. The curve here is convex, right? And the curve here is concave, right? It is going like upwards, and it is now going downwards. So the point here, the curve changes its curvature from concave to convex, or from convex to concave. So we can say that it is the inflection point, and we get the local maxima and local minimum. So I think that you have got the idea how the value of local maxima and local minima can be found out. Just give a thumbs up if you have enjoyed and if you have understood this tutorial. Thank you.